Take a moment right now to let your body settle into wherever you happen to be. Maybe you're tucked beneath the weight of a blanket that feels just right, not too heavy, not too light. Maybe there's a familiar sound in the background, the low hum of a fan, the distant song of wind moving past a window, or simply the deep, unhurried quiet of a late hour. Whatever is around you, let it be as it is. You don't need to change anything. You don't need to be anywhere else. Breathe in slowly, letting your lungs fill gently, like a tide coming in on a calm shore. And breathe out, releasing everything you are carrying today. Your shoulders, if they've crept up toward your ears, can soften downward now. The muscles along your jaw, your temples, the space between your eyebrows, all of these can ease and let go. There's nothing to solve right now. There's nothing urgent. There is only this gentle stretch of time, carved out just for you, quiet and unhurried. Tonight, we are going to take a journey together, not one that requires anything of your body, which is invited to rest completely. Your mind can drift along with the words, picking up whatever feels interesting and allowing the rest to float past like leaves on a slow river. We are going to explore one of the most magnificent, mysterious, and endlessly fascinating questions that human beings have ever asked. Can we actually reach a black hole? It sounds like the stuff of science fiction, doesn't it? Black holes? Those terrifying, beautiful, impossible regions of space where the laws of physics themselves are bent to their breaking point, where time slows and warps, where the fabric of reality folds inward, where even light, the fastest thing in the universe, cannot escape. And yet, these are real. They are out there, scattered across the cosmos, some of them relatively close in astronomical terms, patiently bending space-time, swallowing whatever wanders too near, and posing questions that have kept physicists awake, very much not in the comfortable way you are relaxing now, for decades. So settle in. Let your eyes close if they'd like to. Let the words carry you gently through one of the universe's most extraordinary stories. And when sleep comes to find you, whenever it does, let it take you. The universe will still be here, vast and patient, waiting. If this is your first time here on the Science Pillow, welcome. I am so glad you found your way to this little corner of the universe. This channel exists for exactly this purpose, to take the big, wondrous, sometimes overwhelming questions of science, and to explore them in a way that actually helps you relax. You won't find flashing graphics or urgent countdowns here. You'll find curiosity, calm, and the deep comfort that comes from remembering just how extraordinary the cosmos is, and how extraordinary it is that we get to be tiny, thinking creatures inside it. If tonight's video helps you drift off, or simply gives your mind something beautiful to rest on, I'd love for you to hit that like button before you close your eyes. It sounds like such a small thing, but it genuinely helps this channel reach more people who might be looking for exactly what you found tonight. And if you haven't already, subscribing means the next time you want a long, gentle exploration of something cosmic, historical, or deeply fascinating, you'll find it waiting for you. There's a little bell icon too, if you'd like a quiet notification when new videos arrive, though maybe turn the volume down first. We have a growing library here on the Science Pillow. Past journeys have taken us to the edge of the observable universe, deep into the nature of consciousness and sleep itself. Through the history of how humans first understood that the Earth moves around the sun, and into the strange, dreamy world of quantum mechanics. Every video is designed to be something you can return to again and again. A familiar voice in the dark, a patient companion for the in-between hours. Now, without any further delay, let's begin. Let's ask the question that has fired the imagination of scientists, philosophers, science fiction writers, and anyone who has ever looked up at a night sky and felt that particular, wonderful kind of vertigo that comes from realizing just how much is out there. Can we actually reach a black hole? And what on earth, or rather, what off Earth entirely, would happen if we tried? Part 1. What even is a black hole? Before we can talk about reaching a black hole, we need to spend a little time with the object itself. Because the word gets thrown around so casually in movies and news headlines and casual conversation that it's easy to forget how genuinely strange and radical the idea is. A black hole is not a hole, at least not in any conventional sense. It is not an absence of anything. It is, if anything, it is a concentration of matter so extreme, so unyielding, that it warps the very geometry of space and time around it into something our everyday minds were simply not built to comprehend. The story begins, as so many of the best stories in science do, not with a discovery, but with a thought. It was the year 1784, and an English clergyman, an amateur scientist named John Michell, was sitting with a curious problem. He understood Isaac Newton's laws of gravity, and he understood that light, whatever its true nature, moved at a finite speed. And so he asked a question that sounds deceptively simple. What would happen if a star were so massive, so dense, that the escape velocity from its surface exceeded the speed of light? Escape velocity is the speed you need to achieve in order to pull free of a gravitational field without any further propulsion. To escape Earth's gravity, you need to be moving at about 11.2 kilometers per second. To escape the sun's gravity from its surface, you'd need to be moving at about 617 kilometers per second. Michel reasoned that, for a sufficiently massive object, that escape velocity might exceed 300,000 kilometers per second, the speed of light. And if that were true, then light itself could not escape. The object would appear completely dark, invisible, a dark star. Michel shared this idea in a paper published in 1784, and a similar idea was independently proposed by the French mathematician Pierre-Simon Laplace in 1796. Both men were essentially describing what we now call a black hole, though they were working with Newtonian physics, which doesn't quite capture the full picture. For over a century, the idea was noted, occasionally discussed, and largely set aside. It seemed almost too extreme, too strange to be real. Then came Albert Einstein. In 1915, Einstein published his general theory of relativity, a revolutionary reimagining of gravity that replaced Newton's concept of a force acting at a distance with something far more profound, In Einstein's framework, gravity is not a force at all. It is a curvature in the fabric of space-time itself. Mass and energy warp the four-dimensional structure of space and time, and other objects, including light, follow the curves of that warped geometry. The planets don't orbit the sun because the sun pulls them. They orbit because the sun's mass has curved space-time into a shape that causes them to follow curved paths through it. Almost immediately after Einstein published his equations, a German physicist named Karl Schwarzschild, who was serving on the Russian front during World War I and would die just months later from a skin disease contracted at the front, solved Einstein's equations for the special case of a perfectly spherical, non-rotating mass. And buried in that solution was something extraordinary. At a certain critical radius, now called the Schwarzschild radius, the equations predicted that space-time would curve so severely that nothing could escape. The Schwarzschild radius for our sun, if it were compressed down to that size, would be about 3 kilometers. For the Earth, it would be less than a centimeter. At those densities, the laws of physics as we understand them produce a point of no return. For years, even Einstein himself resisted the implication. He wrote a paper in 1939 arguing that such objects could not actually form in nature. He believed physical processes would always intervene before matter could be compressed so far. But he was wrong. In the following decades, as physicists developed better models of stellar evolution, it became clear that for stars above a certain mass, the end of their lives would produce exactly the kind of object Schwarzschild's equations described. When a massive star exhausts its nuclear fuel, the outward pressure that has been holding it up against gravity collapses. The core implodes with almost unimaginable violence. And for the most massive stars, those with cores above roughly 2 to 3 times the mass of our Sun after the explosion, nothing stops the collapse. The matter keeps falling inward, past the point where neutron degeneracy pressure could halt it, all the way down to a singularity. The term black hole itself was popularized by the American physicist John Archibald Wheeler, who used it in a lecture in 1967. Before that, physicists had been using the ungainly term frozen star, reflecting the strange time dilation effects near these objects. Black hole was more evocative, more visceral, and it stuck. Wheeler was a brilliant communicator and one of the great figures of 20th century physics, and his gift for language gave the world one of its most enduring scientific terms. So what exactly is a black hole in the most precise terms we currently have? It is a region of space-time where the gravitational field has become so strong that the escape velocity exceeds the speed of light. This region is bounded by a surface called the event horizon, named for the metaphorical similarity to the horizon at sea, beyond which you cannot see. The event horizon is not a physical surface. There is no wall, no membrane, no material boundary. It is a mathematical surface in space-time, a threshold, a point of no return defined purely by geometry. Cross it, and every path through space-time that could lead you back out has been eliminated. You are in a one-way region. Every direction of motion, including what was previously outward, now leads only inward toward the singularity at the center. And the singularity itself is where our understanding runs out. General relativity predicts it as a point of infinite density and infinite space-time curvature. But physicists generally regard this as a signal that the theory has broken down, that we are asking it questions beyond its domain of validity. At the scale of the singularity, quantum mechanical effects would become crucial, and we don't yet have a successful theory of quantum gravity that can describe what happens there. It's one of the most important open questions in all of physics, and we'll return to it later in the evening. For now, hold on to this core image. A black hole is a region of space where gravity has become so extreme that the very geometry of space-time prevents escape. Not because of some material barrier, not because of any force reaching out and grabbing you, but simply because of the shape of space and time in that region. Even light, following the straightest possible paths through curved space-time, curves inward and never finds its way out. It's the most elegant prison imaginable, one built from the fundamental structure of the universe. And these objects are real. They are not just theoretical curiosities confined to the pages of physics journals. They are out there right now, scattered through the galaxy by the hundreds of millions, bending light, swallowing gas, sometimes tearing apart whole stars that wander too near, and anchoring the centers of nearly every large galaxy in the observable universe. The black hole at the center of our own Milky Way, a giant called Sagittarius A star, has a mass of about 4 million times the mass of our Sun, and we even have a photograph of it now, or rather, a photograph of the glowing gas swirling around it, the shadow it casts against that glow. More on that remarkable achievement later. Part 2. The many faces of black holes. Not all black holes are alike. They come in a stunning range of sizes, and each size class has its own story, its own formation mechanism, and its own role in the larger cosmic drama. Astronomers broadly divide black holes into 4 categories, though the boundaries between them are somewhat fluid and still debated. The most common type, and the kind most of us picture when we think of a black hole, is the stellar mass black hole. These are the descendants of massive stars, cosmic beasts that lived fast and died violently. When a star with a mass somewhere between roughly 8 and several hundred times that of our Sun exhausts the hydrogen fuel at its core, a chain of events is set in motion that leads, in some cases, to a black hole. The star has been spending its entire life in a delicate balance, the outward pressure of nuclear fusion pushing against the inward pull of gravity. When fusion stops, gravity wins. The outer layers of the star collapse inward at tremendous speed, then rebound in a cataclysmic explosion called a supernova. For a brief period, a supernova can outshine an entire galaxy of hundreds of billions of stars. But the fate of the core depends on its mass. If the core is between roughly 1.4 and 2 to 3 solar masses, after the collapse, it can become a neutron star, an object so dense that a teaspoonful of its matter would weigh hundreds of millions of metric tons on Earth, held up by the quantum mechanical pressure of tightly packed neutrons. But if the core exceeds that limit, there is no force in the universe capable of stopping further collapse. The matter falls all the way down, and a black hole is born. Stellar mass black holes typically range from about 5 to perhaps 50 solar masses. although the upper limit is still debated. Gravitational wave detectors like LIGO and Virgo have now detected dozens of events caused by merging stellar black holes, and some of the merging pairs have masses that push our theoretical models. In September 2015, LIGO detected gravitational waves from two black holes, one 36 solar masses, the other 29, spiraling together and merging into a single 62 solar mass black hole with the energy equivalent of 3 solar masses radiating away as gravitational waves in a fraction of a second. It was a triumph of physics and engineering alike. The Milky Way alone is estimated to contain somewhere around 100 million stellar mass black holes. Most of them are completely invisible, quietly lurking in the darkness of space, their presence only detectable if they happen to be close to a companion star, drawing material off it and producing X-rays, or if they happen to merge with another compact object and produce gravitational waves that ripple across the universe and eventually, ever so faintly, squeeze and stretch the mirrors of our detectors. At the other extreme are the supermassive black holes, and they are extraordinary objects by any measure. Instead of a few tens of solar masses, supermassive black holes have masses ranging from hundreds of thousands to tens of billions of times the mass of our Sun. The largest known, a monster called Ton 618, located about 10.4 billion light-years away, has a mass of about 66 billion solar masses. Its event horizon has a diameter of roughly 130 billion kilometers, about 40 times larger than the orbit of Neptune around our Sun. Wrapped up inside that event horizon is more mass than the entire Milky Way's complement of stars. These giants live at the centers of galaxies. Almost every large galaxy has one, and their mass is mysteriously correlated with the properties of the galaxy around them, suggesting that the black hole and the galaxy grow together, each influencing the other. The black hole at the center of our Milky Way, Sagittarius A star, is relatively modest as supermassive black holes go, at about 4 million solar masses. The black hole at the center of the giant elliptical galaxy, M87, which we now have a famous photograph of, is 6.5 billion solar masses. One of the largest known in a nearby galaxy, in a galaxy called Holmberg 15A, is at least 40 billion solar masses. How supermassive black holes formed is still one of the most active questions in astrophysics. They couldn't have grown from stellar mass black holes by slowly accreting matter over billions of years, because we now know they existed already when the universe was less than 1 billion years old, and there simply wasn't enough time for that process to work. They must have had a head start, whether from the direct collapse of enormous primordial gas clouds or from the merger of many smaller black holes in dense early star clusters, or from some other process we haven't fully worked out yet. Between stellar and supermassive lies the category of intermediate mass black holes, ranging from roughly 100 to 100,000 solar masses. For a long time, astronomers wondered if these objects actually existed, since there was no obvious formation mechanism. But in recent years, gravitational wave observations and careful studies of dense star clusters, called globular clusters, have provided growing evidence that intermediate mass black holes are real, if rare. In 2020, LIGO detected gravitational waves from a merger that produced a black hole of about 142 solar masses, placing it firmly in the intermediate mass range. These objects are thought to form either through the repeated mergers of stellar black holes in dense environments, or through the collapse of very massive stars in the early universe. The fourth and most speculative category is primordial black holes. These would have formed not from stellar collapse, but from the extreme densities of the very early universe, less than 1 second after the Big Bang. In that unimaginably hot, dense environment, quantum fluctuations could have created regions dense enough to collapse directly into black holes before any stars or galaxies existed. Primordial black holes could theoretically span an enormous range of masses, from the nearly microscopic to thousands of solar masses. Intriguingly, some physicists have proposed that primordial black holes of certain masses could account for some or all of the universe's dark matter, that mysterious substance that makes up about 27% of the universe's total mass and energy, but doesn't interact with light in any way we can detect. No primordial black holes have been definitively identified, but the search continues. What all four types share, the defining feature that makes a black hole, is the event horizon, the boundary of no return. The physics inside that boundary, the strange reality of a region where every direction leads inward, where time itself moves differently, is the same regardless of whether the black hole weighs 10 times the mass of our sun or 10 billion times. It's a reminder that the universe is, at some level, elegantly consistent, that the same equations and the same fundamental principles apply from the smallest to the most gargantuan of these extraordinary objects. And there's one more thing worth noting, something that surprises many people when they first encounter it. A black hole is not a cosmic vacuum cleaner. It does not reach out and grab things from a distance. If our sun were replaced by a black hole of the same mass, Earth would continue in its current orbit, utterly unchanged, circling the dark remnant at exactly the same distance and speed as before. The planets would not spiral inward. The gravitational pull of a black hole at any given distance is exactly what you'd expect from an object of that mass, no more and no less. The difference is that you can get much closer to a black hole than you could to a star of the same mass, because the black hole has no physical surface to stop you. You can approach all the way to the event horizon, and only then does the universe become unescapably strange. Part 3. The nearest black holes and what it would take to reach them. Now that we have a sense of what black holes are and the extraordinary variety they come in, let's ask a more immediate, more personal question. How far away are the nearest ones? And when we talk about reaching a black hole, what distances are we actually discussing? For most of human history, we had no idea where any individual stellar black hole was. We could infer the existence of black holes in X-ray binary systems, where a stellar mass black hole is close enough to a companion star to draw material off it, creating a hot, glowing accretion disk that shines in X-rays. But those systems are all thousands of light years away, and many of them are identified by their X-ray emissions, which means the black holes we found first were specifically the active, feeding ones, the quiet ones, the vast majority that are simply sitting in the dark, without any nearby companion to feed on, were essentially invisible. That began to change in a remarkable way with the European Space Agency's Gaia satellite, launched in 2013. Gaia's mission is to create the most precise map of the Milky Way ever assembled, measuring the positions, distances, and motions of over 1 billion stars with extraordinary precision. And buried in that ocean of stellar data were hints of something unusual. Stars that appeared to be orbiting nothing. Their paths through space showed the gravitational signatures of a massive unseen companion. A companion that gave off no light. In 2022, astronomers using Gaia data and follow-up ground-based observations identified a system now known as Gaia BH1. It lies about 1,560 light-years from Earth in the constellation Ophiuchus, and it contains a black hole of approximately 10 solar masses orbiting in a binary pair with a Sun-like star. At 1,560 light-years, it is the closest confirmed black hole to our solar system yet discovered. To give that distance some context, light from Gaia BH1 takes 1,560 years to reach us. The photons entering our telescopes right now left that system around the time of the early medieval period on Earth. Shortly after, in 2023, a second system was identified, Gaia BH2, located about 3,800 light-years away in the constellation Centaurus. And then in April 2024 came the most dramatic discovery yet, Gaia BH3 in the constellation Aquila, lying about 1926 light-years from Earth. What made this one especially striking was its mass. Gaia BH3 weighs in at approximately 32.7 solar masses, making it the most massive stellar black hole ever found in the Milky Way. A star nearly 33 times the mass of our Sun collapsed into a dark remnant that now quietly orbits its companion, invisible except through the careful measurement of that companion's dancing path through space. These are the nearest confirmed stellar black holes, but astronomers suspect there are many more waiting to be found as Gaia continues its survey. One theoretical estimate from astrophysicist Avi Loeb at Harvard University suggested that the nearest black hole at any given time might actually be as close as about 30 light-years, embedded somewhere in the dense crowd of stars in our immediate galactic neighborhood. At that distance, a spacecraft capable of traveling at half the speed of light could reach it within a human lifetime. With our current best technology, chemical rockets and ion drives, it would take approximately 1 million years. 1 million years. That number deserves to sit quietly for a moment while you breathe. Our entire recorded history, from the first writing systems in ancient Mesopotamia to the civilization we have built today, spans roughly 5,000 years. 1 million years is 200 times that stretch of time. It is the span across which the human species itself has changed enormously. Since 1 million years ago, our ancestors were Homo erectus, bipedal and tool-using, but separated from us by an almost incomprehensible gulf of evolutionary and cultural change. And that would be the travel time, using rockets not fundamentally different from what we use today. And that's just to reach the nearest possible stellar black hole. Sagittarius A star, the supermassive black hole at the center of our galaxy, is 26,000 light-years away. Even traveling at the speed of light, a journey we know to be physically impossible for any object with mass, that trip would take 26,000 years. It's a distance that simply demolishes the scale of human civilization and human lifespan. So we are, in the most blunt and honest sense, extraordinarily far from any black hole. The cosmos that contains these extraordinary objects also places them at distances that mock every propulsion system we have ever built. And yet, as we'll explore in the next part of tonight's journey, this situation is not entirely without hope. The technology that might one day change this calculation is not entirely in the realm of science fiction. There are people working on it right now, and the story of what they're imagining is remarkable. Before we leave the question of distances behind, it's worth pausing on one more comparison, because the numbers are so striking that they deserve more than just a quick mention. The fastest human-made spacecraft ever launched was the Parker Solar Probe, which has achieved speeds of up to about 692,000 kilometers per hour in its close approaches to the Sun. That sounds extraordinarily fast, and in any human frame of reference, it is. But light travels at about 1.08 billion kilometers per hour. The Parker Solar Probe moves at about 1/1500th of the speed of light. At that speed, a journey to Gaia BH1, just 1,560 light-years away, would take roughly 2.44 million years. A ship moving at that pace would need to have been launched when Homo habilis was walking the African savanna for the very first voyage, to just now be arriving. The scale of these distances is not a bug in the universe's design. It's a feature. It's the feature that has kept us safe here on this warm, rocky world, while the cosmic drama of exploding stars, merging black holes, and gamma-ray bursts plays out around us at safe remove. But it's also the feature that makes black hole travel feel, for now, like a dream only the most distant and advanced future civilization might achieve. Part 4. The dream of getting there, proposed missions, and future technology. If the distances to black holes are so immense and our current technology so inadequate, is there any realistic path forward? This is where the story becomes genuinely exciting, because in 2025, a physicist named Cosimo Bambi at Fudan University in Shanghai published a paper in the journal iScience that proposed something remarkable: an interstellar mission to a black hole that, while deeply challenging and highly speculative, is not completely unrealistic. The key to Bambi's proposal is a class of technology called nanocrafts, tiny spacecraft, about the mass of a paperclip, consisting of a microchip and a light sail. The idea builds on the vision of Breakthrough Starshot, a research initiative backed in part by physicist Stephen Hawking and billionaire Yuri Milner, which proposed sending such nanocrafts to Alpha Centauri, our nearest stellar neighbor, at 4.24 light-years away. The concept is audacious and elegant. Instead of carrying fuel, the spacecraft uses a huge sail made of extremely thin, reflective material. A powerful array of ground-based lasers fires a concentrated beam of photons at the sail, and the pressure of that light accelerates the craft to incredible speeds. Breakthrough Starshot's goal is to accelerate nanocrafts to about 20% of the speed of light. At that speed, a trip to Alpha Centauri would take roughly 20 years. Bambi's vision is similar, but aimed at a nearby black hole rather than a star. For a target black hole somewhere between 20 and 25 light years away, and there are no confirmed black holes that close today, though the theoretical calculations suggest there could be undiscovered ones in that range. A nanocraft traveling at about 1/3 of the speed of light could reach it in approximately 60 to 75 years. The data it gathered and transmitted back to Earth would take another 20 to 25 years to arrive, making the total mission duration somewhere between 80 and 100 years. A century-long mission, longer than a human lifetime, but not longer than a civilization's patience, and not longer than the persistence of an international scientific collaboration that has already demonstrated it can sustain effort across decades. The Event Horizon Telescope, which produced the first images of black holes, was a project that developed over more than a decade of incremental technical progress. The Voyager probes, launched in 1977, are still operating and communicating with Earth nearly 50 years later. A century-long mission to a black hole is extraordinary, but it's not obviously beyond the kind of institutional commitment that the best of human science can manage. There are enormous obstacles, of course. The laser array needed to accelerate even a gram-mass nanocraft to 1/3 the speed of light would need to be extraordinarily powerful. Bambi estimates that with current technology, such a laser array would cost around 1 trillion euros. That is clearly impossible today, but the cost of laser technology has been falling rapidly, roughly halving every 4 years in terms of cost per coherent watt. On that trajectory, within 30 years, the cost might fall to around 1 billion euros, which is comparable to the budget of major space missions today. This is not guaranteed, but it's within the range of possibility. Then there's the question of the spacecraft itself. A paperclip mass craft capable of surviving interstellar travel for decades needs to be extraordinarily resilient. At 1/3 of the speed of light, even a single hydrogen atom impacts with enormous energy. And interstellar space, while almost incomprehensibly empty, does contain a thin scattering of gas and dust. The craft would need materials capable of withstanding decades of such bombardment, along with cosmic radiation and the cold of deep space. It would need instruments sensitive enough to measure the properties of a black hole, and a communication system capable of transmitting data across tens of light years. None of these technologies exist today in the forms needed, but none of them are obviously impossible. Another fascinating concept for reaching, or at least approaching, a black hole comes from astrophysicist David Kipping at Columbia University, who proposed what he calls the halo drive. This concept builds on the century-old idea of using a gravitational slingshot maneuver around a massive object to gain speed. The halo drive takes this further by imagining a spacecraft that approaches the ergosphere of a rapidly spinning black hole, a region just outside the event horizon, where space-time itself is dragged around by the black hole's rotation like honey swirling around a spoon, and uses a reflected laser beam in conjunction with this frame-dragging effect to extract energy from the black hole's rotation. In theory, a civilization with the right technology could use a black hole as a virtually inexhaustible energy source and propulsion system, gaining speed in passes by the rotating black hole until reaching a significant fraction of light speed. There are also, in the realm of speculation but not of outright impossibility, the concepts of antimatter rockets and nuclear pulse propulsion. Antimatter rockets, which would generate thrust through matter-antimatter annihilation, would be theoretically capable of reaching speeds that are a significant fraction of light speed. The energy released when matter meets antimatter is the most efficient conversion of mass to energy possible. 100% efficient compared to nuclear fission at less than 1% and chemical combustion at a fraction of a percent. The problem is manufacturing antimatter in the quantities needed. The particle accelerators at CERN produce tiny amounts of antihydrogen at extraordinary expense and difficulty. Scaling that up to the tons of antimatter a starship would need is a challenge almost beyond imagining with current physics and engineering. Nuclear pulse propulsion, in the form of the old Project Orion concept from the late 1950s, proposed detonating small nuclear devices behind a spacecraft and riding the shock wave. The idea is crude, but would work, and theoretical studies suggested it could achieve speeds of perhaps 3 to 10% of the speed of light. Modern variants, using laser-ignited nuclear fusion, like Project Daedalus from the 1970s, proposed reaching perhaps 12% of light speed. These are all far slower than what Bambi's nanocraft approach would achieve, but they have the advantage of potentially carrying a larger payload, a probe capable of more sophisticated measurements, or even, in the very distant imaginings of futurists, a crewed vessel. What's striking about all of these proposals is the gap between what we can dream and what we can currently do. That gap is enormous, but it has always been enormous. In 1903, the Wright brothers flew for 12 seconds at Kitty Hawk. 66 years later, humans walked on the moon. In 1957, the first Earth-orbiting satellite weighed about 83 kilograms and lasted 21 days. 12 years later, humans were on the moon. The history of aerospace is a history of bridging apparently impossible gaps through sustained human ingenuity. Whether we can bridge the gap from chemical rockets to interstellar nanocrafts in the next century is genuinely, but the people working on these ideas are serious scientists and engineers, not dreamers in garages. And the mathematics, at least, is not telling us no. Bambi's paper ends with a thought that echoes across the history of impossible-seeming achievements in physics and astronomy. He notes that people once said we would never detect gravitational waves, that the signals would be too faint, the technology too limited. Then, in 2015, after decades of work, LIGO detected them for the first time. People once said we would never image a black hole directly. Then in 2019, the Event Horizon Telescope revealed the glowing ring around the void at the heart of M87. Each time, what seemed impossible became merely difficult, and then it became done. Part 5. What would you experience on the journey? Let's indulge ourselves for a little while and imagine that the technology problem has been solved. Perhaps it's 50 or 80 or 150 years from now, and humanity has developed laser-propelled nanocrafts or fusion-powered starships capable of reaching a significant fraction of the speed of light. A mission to the nearest black hole has been launched. Perhaps you are along for the ride in some future form, perhaps as data patterns running on the ship's computer, or perhaps the mission profile allows for a crewed vessel with suspended animation. Let's imagine the journey. What would you encounter on the way? The first thing you'd notice after the initial acceleration phase is the silence and the dark. Interstellar space is almost incomprehensibly empty. The density of atoms in the interstellar medium, the thin gas between the stars, averages about 1 atom per cubic centimeter. To put that in perspective, the air you're breathing right now contains approximately 10 to the 19th power atoms per cubic centimeter. The interstellar medium has perhaps 19 orders of magnitude fewer particles per unit volume than the air in your bedroom. It is as close to a perfect vacuum as anything we encounter in our natural experience of the universe. This emptiness means that interstellar space is also extraordinarily cold. Without any dense matter to carry heat, the background temperature of the universe is just 2.7 degrees. Above absolute zero, the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Your ship, streaming through this void at perhaps 30% of light speed, would be surrounded by a darkness of almost absolute depth, punctuated only by the stars. But those stars would look very different from what you see from Earth. At relativistic speeds, a phenomenon called aberration causes stars to appear to shift toward the direction of travel. If you're moving toward the constellation of Eucus, where Gaia BH1 lies, the stars in front of you would appear to cluster and concentrate, while the stars behind you would spread and thin. This effect becomes more pronounced as you approach the speed of light. At high enough fractions of light speed, all the stars in the universe would appear squeezed into a bright, glowing ring in the direction of travel. Alongside aberration comes another relativistic effect, blue shift in the forward direction, and redshift in the backward direction. Light from the stars ahead of you would have its wavelengths compressed, shifting toward shorter wavelengths, toward violet and then ultraviolet and X-ray. Light from the stars behind would be stretched toward longer wavelengths, toward infrared and then radio. The light show of a relativistic flight through interstellar space would be unlike anything seen from a stationary vantage point. There is also the matter of time. Einstein's special theory of relativity predicts that moving clocks tick more slowly relative to stationary ones, a phenomenon called time dilation. At 30% of the speed of light, time dilation is modest but real, causing clocks on the ship to run about 4.8% slower than clocks on Earth. A journey of 75 years of ship time would correspond to about 79 years on Earth. At higher fractions of light speed, the effect becomes dramatic. At 99% of light speed, time dilation means that 1 year of ship time corresponds to over 7 years on Earth. At 99.9% of light speed, the ratio is about 22 to 1. theoretical expeditions to nearby stars could, if the ship could be accelerated to very high fractions of light speed, be accomplished in ship years even if Earth's centuries passed in the meantime. This is not a small or abstract detail. If humanity ever achieves true relativistic interstellar travel, time dilation means that the crew of such a vessel would age slowly while entire generations passed on Earth. A crew member who embarked on such a journey might return to find their children aged beyond recognition, their world changed beyond familiarity. It's a poignant dimension of what relativity does to time, and it has inspired some of the most emotionally resonant science fiction ever written. Another hazard of high-speed interstellar travel is cosmic rays. High-energy particles, mostly protons accelerated by supernova remnants, and other energetic events, stream through space constantly. On Earth, the planet's magnetic field and atmosphere provide substantial protection. In interstellar space, with no such shield, cosmic ray exposure would be significant. At relativistic speeds, individual hydrogen atoms in the interstellar medium would impact the ship with enough energy to be themselves a form of radiation. The Parker Solar Probe, moving at merely a tiny fraction of light speed, needs no such radiation shielding. A relativistic starship would need engineering solutions we haven't fully developed. And then there's the sheer duration of the journey. Even the optimistic scenario, a nanocraft reaching a black hole 20 to 25 light-years away in 70 years, involves 70 years of continuous autonomous operation. The ship would need to navigate, maintain itself, collect data, and communicate with Earth entirely autonomously for that entire period. Communication itself would be increasingly delayed, up to 25 years of delay each way for signals sent from the destination. The humans who planned and launched the mission would be dead by the time the first scientific data arrived. This is a kind of intellectual and institutional commitment that we haven't demonstrated before at anything like that scale. But it's the kind of commitment that the great cathedrals of medieval Europe were built on, generation after generation, contributing to a project none would see completed. As the ship approaches the target system and begins to detect the presence of the black hole, the instruments would begin returning data unlike anything gathered from afar. Gravitational wave detectors on board might sense the faint ripples from the black hole's interactions with nearby matter. Measurements of the curvature of space-time itself would confirm the black hole's mass and spin with extraordinary precision. And eventually, as the ship entered the region close enough for direct observation, something remarkable would happen. The universe around the approaching probe would begin to look different in a way that no camera pointed at the black hole from Earth has ever captured. Part 6. Approaching the event horizon. What you'd see and feel as any spacecraft or hypothetical traveler approaches a black hole. The experience would be unlike anything else in the universe. Not immediately dangerous, not immediately dramatic, but quietly, profoundly strange. Let's trace that approach from the relatively far to the terrifyingly close. The first sign of the black hole's presence, long before any visual confirmation, would be gravitational. The black hole's gravity would begin to influence the craft's trajectory in ways that would need to be carefully accounted for. This is not the crushing, destructive gravity of popular imagination. At large distances, the gravitational field of even a stellar mass black hole is no different from the gravitational field of an ordinary star of the same mass. The danger is not the strength of the field, but the gradient, the difference in gravitational pull between different parts of an object. As you close the distance, visual effects would begin to manifest. The black hole itself would appear as a dark, circular region against the background of space, like a perfectly round hole cut out of the starfield. But surrounding it would be light, the light from stars and gas behind the black hole, bent by its extreme gravity into extraordinary configurations. Einstein's general relativity predicts, and observations have confirmed, that massive objects act as gravitational lenses, bending the paths of light rays passing near them. Near a black hole, this lensing becomes extreme. Stars that are actually behind the black hole, that you'd normally never see because the black hole is in the way, would appear to have been pulled around and to the side, distorted into arcs or even complete rings, called Einstein rings. You might see multiple images of the same star scattered at different positions around the black hole's dark silhouette, each image created by light that took a different curved path around the black hole before reaching your eye. The star field around the black hole would be warped, stretched, and duplicated in ways that simply do not happen anywhere else in the universe. Closer still, you'd begin to see the accretion disk, if the black hole has one. Not all black holes do. The quiet, isolated ones like Gaia BH1 have no nearby material to feed on and are truly dark. But if there's gas or material falling in, it forms a flattened, rotating disk of superheated plasma that glows brilliantly across much of the electromagnetic spectrum. The temperature in the inner regions of an accretion disk can reach tens of millions of degrees, making it glow in X-rays. The outer regions are cooler, radiating in ultraviolet and visible light, and the disk would not look the way it's typically depicted in textbook illustrations. Because the black hole's extreme gravity bends light so severely, you'd see not just the front face of the disk, but also the back. Light from the far side of the disk, which is behind the black hole from your perspective, would be bent over the top and under the bottom of the black hole, appearing as a bright arc above and below the dark central region. This is the characteristic ring of light that the Event Horizon Telescope captured in its famous images of M87's black hole and our own Sagittarius A star. Up close, the effect would be even more dramatic. There exists at a particular distance from any black hole a sphere called the photon sphere, where gravity is strong enough to make light orbit in circles. At the photon sphere, a beam of light sent perfectly tangentially to the black hole would travel around it in a circle indefinitely, or until it was disturbed. For a non-rotating black hole, the photon sphere lies at 1.5 times the Schwarzschild radius, or 1.5 times the radius of the event horizon. An observer approaching this region would be in an extraordinarily strange environment, where light from the rest of the universe would seem to pile up and concentrate around the edges of the dark region ahead. Beyond the photon sphere, there is a boundary called the innermost stable circular orbit, or ISCO. This is the closest distance at which matter can remain in a stable orbit around the black hole. Material inside the ISCO is on an inevitable inward spiral drawn toward the event horizon. For a non-rotating black hole, The ISCO lies at 3 times the Schwarzschild radius, or 3 times the radius of the event horizon. For a rapidly rotating black hole, the ISCO can be much closer to the event horizon. This is where the accretion disk has its inner edge, and it's one of the most energetically extreme environments in the universe, where material is moving at nearly the speed of light in a region of extreme gravitational curvature. One of the most striking phenomena that a traveler approaching a black hole would experience is gravitational time dilation, a real measurable effect with genuine consequences. General relativity predicts that time passes more slowly in stronger gravitational fields. This has actually been measured here on Earth. Atomic clocks at sea level tick very slightly slower than identical atomic clocks at the top of a mountain because sea level is slightly deeper in Earth's gravitational field. The GPS satellites orbiting Earth tick slightly faster than identical clocks on the surface, and their signals must be corrected for this effect for GPS to work accurately. Near a black hole, gravitational time dilation becomes extreme. If you hovered at a fixed distance close to the event horizon, maintained there by powerful rockets that prevented you from falling in, you would experience time passing at a much slower rate than someone far away from the black hole. Clocks ticking at your location would appear, to the distant observer, to tick incredibly slowly. If, in a thought experiment, you hovered just outside the event horizon for what felt to you like 1 hour, years or centuries or millennia could pass on Earth, depending on exactly how close to the event horizon you were. The movie Interstellar played with this idea memorably, with the planet near the black hole experiencing an hour for every 7 years elsewhere, though that was at a safe orbital distance rather than a hover near the event horizon. From the perspective of the person falling freely into a black hole, as opposed to someone hovering at a fixed distance, time dilation works differently. A freely falling observer doesn't feel the extreme gravitational field as a local effect at all. They're in free fall, weightless, following the curvature of space-time just as the orbiting International Space Station is in free fall around Earth and its astronauts are weightless. The experience of crossing the event horizon for a freely falling observer, particularly one falling into a supermassive black hole, might be surprisingly unremarkable, at least locally. We'll come back to that. Part 7. Spaghettification and the point of no return. And now we come to the part of the journey that, depending on which kind of black hole, would either be the final moments of your experience or, strangely, might pass almost unnoticed at first. Spaghettification. The word is genuinely scientific, not a joke, not a casual metaphor, but the actual technical term used in the physics literature for the process by which tidal forces near a black hole stretch matter into long, thin strands. The concept comes from tidal forces, which are a feature of any gravitational field that varies from place to place. On Earth, the moon's gravity creates ocean tides because it pulls slightly harder on the side of Earth closest to the moon than on the far side. The net effect is a stretching force that creates 2 tidal bulges in Earth's oceans. The same principle applies to any extended object in a varying gravitational field. Now imagine being oriented feet first toward a black hole. Your feet are closer to the black hole than your head. Because gravity follows an inverse square law, your feet experience a stronger gravitational pull than your head. The difference in that pull creates a stretching force along the length of your body. At the same time, the gravity pulling your left side and your right side toward the center of the black hole slightly squeezes you horizontally. The net result is exactly what the name implies. You would be stretched vertically and compressed horizontally, like a piece of dough being pulled into a thin strand. Whether this process kills you before you reach the event horizon depends entirely on which kind of black hole you're approaching. Here's the counterintuitive part. Larger black holes are less immediately deadly than small ones. At the event horizon, this seems backward at first, because surely more massive black holes have stronger gravity. But the key is not the strength of the gravity, but the gradient, the rate at which gravity changes over the distance of your body. For a stellar mass black hole of, say, 10 solar masses, the event horizon would have a radius of about 30 kilometers. The difference in gravitational pull between your head and feet at that radius, separated by perhaps 2 meters, is enormous. The tidal forces at the event horizon of a solar mass black hole would be so strong that you'd be stretched into a thin stream of atoms long before you ever crossed it. The spaghettification would happen at a safe distance outside the event horizon, and it would be instant, catastrophic, and complete. But for a supermassive black hole of several million solar masses, like Sagittarius A star, the event horizon has a radius of about 12 million kilometers. The difference in gravitational pull between your head and your feet at that distance is tiny. The tidal force at the event horizon of Sagittarius A star would be comparable to the difference in gravity between your head and your feet standing on the surface of Earth, a difference you experience every day and don't notice. You would cross the event horizon of a supermassive black hole, feeling nothing unusual, no sudden sensation, no obvious boundary, no warning bell, just the faintest, barely perceptible whisper of a tidal force that would only become lethal much, much later as you fell deeper toward the singularity. This is one of the most remarkable features of large black holes. They are, in a specific and important sense, more subtle in their deadliness than small ones. You could cross the event horizon of a billion solar mass black hole and feel absolutely nothing different, at least locally. The spaghettification would come eventually as you fell deeper and the tidal forces grew. But at the moment of crossing that defining boundary, it would be invisible. From the outside, however, things look very different. An observer watching you fall into a black hole would see something extraordinary and permanent. As you approach the event horizon, the light you emitted would become increasingly red-shifted, stretched to longer and longer wavelengths by the extreme gravitational field. You would appear to move more and more slowly as time dilation became more severe. To the distant observer, you would never quite cross the event horizon. You would appear to slow and fade and redden until the light you emitted became too faint and too red to detect. You would appear to freeze like an insect caught in amber, hovering forever just above that boundary, eternally falling but never arriving. But from your own perspective, falling freely, you would cross the event horizon in a perfectly finite amount of time. you would not experience yourself slowing down. You would not see yourself freeze. You would cross the boundary seamlessly, without any local sensation, and begin your fall toward the singularity. The discrepancy between what the distant observer sees and what you experience is one of the most philosophically vertiginous aspects of black hole physics. A place where the relativity of simultaneity and the curvature of space-time produce genuinely irreconcilable descriptions of the same sequence of events. Once inside the event horizon, the geometry of space-time has changed in a fundamental way. In ordinary space-time, you can choose to move in any spatial direction, but you must always move forward in time. Inside a black hole's event horizon, the roles of space and time swap. The singularity is not in any spatial direction. It is in the future. You cannot avoid it any more than you can avoid next Tuesday. Every path forward in time leads toward it. You could fire rockets in any direction, and all you'd accomplish is reaching the singularity at a slightly different location or a slightly different time. There is no trajectory that avoids it. How long you'd have between crossing the event horizon and reaching the singularity depends on the mass of the black hole. For a stellar mass black hole, it would be fractions of a millisecond. For Sagittarius A star, it would be about 20 seconds of proper time. For the largest supermassive black holes, it might be hours. In every case, it would be finite, and it would be one way. Once inside, no signal, no particle, no information of any kind can cross back out. The black hole has taken you completely. Part 8. Inside the black hole, the greatest mystery in physics. And now we step into the territory where science truly meets its limits. What happens inside a black hole? What lies beyond the event horizon? What is the singularity, really? These are questions that current physics cannot fully answer. Not because we lack data in the conventional sense, but because the singularity represents a place where general relativity, our best theory of gravity, predicts its own breakdown. The equations return infinite values for density and curvature, which is physics' polite way of saying, we don't know what's happening here. In the framework of classical general relativity, the singularity is a genuine endpoint. All matter, all information, all structure falls into it and is crushed to a mathematical point of zero volume and infinite density. Time literally comes to an end there. The equations have no extension beyond it. In a very precise sense, there is no inside of a singularity in general relativity, because the singularity is a boundary where the space-time manifold simply stops. But most physicists believe that the true story is more subtle and more interesting. General relativity is an extraordinarily successful theory, verified to extraordinary precision in innumerable experiments and observations. But it is not a quantum theory, and everything we know about physics suggests that, at scales small enough that quantum effects become important, general relativity must be replaced by something more fundamental. A theory of quantum gravity that properly incorporates both the curved space-time of Einstein and the uncertainty and discreteness of quantum mechanics. We don't have that theory yet. There are candidates. String theory and loop quantum gravity are the two most developed ones. but neither has been experimentally confirmed, and the energy scales at which their predictions differ from conventional physics are far beyond what any conceivable particle accelerator could reach. The singularity is precisely the environment where quantum gravity would dominate, and until we have a working theory of quantum gravity, the singularity remains fundamentally mysterious. What loop quantum gravity suggests, in a heuristic sense, is that space itself has a minimum size, a fundamental graininess at scales around the Planck length, which is about 10 to the negative 35 meters, incomprehensibly small. At these scales, the concept of a dimensionless geometric point, like the singularity, may not be physically meaningful. Some models suggest that instead of a singularity, the collapsing matter reaches a maximum density and then bounces, creating a new expanding region that might look from the inside like a baby universe, disconnected from our own, but born from the black hole's interior. These are genuinely speculative ideas, but they're grounded in serious mathematics. String theory approaches the problem differently, replacing point particles with tiny vibrating strings and adding extra dimensions to space-time. In some string theory models, the singularity is replaced by a more complex structure, and the interior of a black hole might be connected to other regions of space-time through structures called wormholes, or might be described by a dual, holographic theory that lives on the event horizon surface rather than in the interior. This brings us to the black hole information paradox, one of the deepest and most debated problems in theoretical physics. In quantum mechanics, information is conserved. If you know the complete quantum state of a system at one moment, you can, in principle, reconstruct its complete quantum state at any earlier or later moment. The laws of quantum physics are time reversible. Nothing is truly erased, but black holes seem to violate this. Stephen Hawking showed in the 1970s that black holes emit thermal radiation through a quantum mechanical process, now called Hawking radiation, gradually losing mass and eventually evaporating completely. If the radiation that carries away the black hole's mass is purely thermal, containing no information about what fell into the black hole, then when the black hole is gone, the information about everything that fell into it is gone too, permanently destroyed. This would violate the most fundamental principles of quantum mechanics. Hawking himself initially believed information was destroyed in black holes, and he made famous bets on the question. But as the decades passed and physicists studied the problem from many angles, the consensus shifted. The holographic principle, developed in the 1990s by Gerard Hooft and Leonard Susskind, suggested that all the information inside a black hole might be encoded on its event horizon, like a three-dimensional object being represented by a two-dimensional hologram. In this view, information isn't truly lost. It's stored at the boundary and eventually returned in some scrambled form through Hawking radiation. In 2012, a group of physicists proposed the firewall paradox, which sharpened the tension in a dramatic way. They argued that if information must be preserved, then the surface of the event horizon must be a place of extremely high energy, a firewall that would destroy anything crossing it. This directly contradicts general relativity's equivalence principle, which says that a freely falling observer should experience nothing special at the event horizon of a large black hole. You can't have it both ways, they argued. Either information is preserved and the event horizon is a fiery death zone, or information is destroyed and quantum mechanics is... The firewall paradox sparked an enormous amount of research and debate, and it hasn't been fully resolved. In 2019, a new approach using a concept called the page curve and quantum extremal surfaces provided evidence that information is indeed preserved, but the detailed mechanism remains unclear. Most physicists today believe that information is not lost in black holes, but understanding exactly how it escapes and what happens at the singularity requires a theory of quantum gravity that we don't yet have. There's something deeply satisfying in a way about this situation. We are living in a moment when the greatest minds in physics are wrestling with questions that genuinely don't have answers yet. Not for lack of trying, not for lack of cleverness, but because the universe is in this particular corner, still keeping its secrets. The singularity, the firewall, the fate of... These are places where the next great revolution in physics is waiting to happen. The breakthrough that might one day give us a complete picture of what happens at the very center of the most extreme gravitational objects in the universe. Part 9. Hawking Radiation and the Infinite Patience of Black Holes. We've talked about the interior of black holes, the spaghettification, the event horizon, the mysterious singularity. But there's one more chapter to this story, a chapter that takes place on an almost incomprehensible timescale and that reveals something both humbling and strangely comforting about the ultimate fate of these extraordinary objects. Black holes are not eternal. They evaporate. This remarkable insight came from Stephen Hawking in 1974. When he combined general relativity with quantum field theory in a landmark calculation that revealed something the classical theory had completely missed. Quantum mechanics tells us that what we think of as empty space is not truly empty. At the tiniest scales, space is a seething, bubbling froth of quantum fluctuations, where pairs of virtual particles spontaneously appear and then annihilate in a time too short to be directly observed. This is not a metaphor or a mathematical trick. The vacuum energy these fluctuations represent has real, measurable effects, including the Casimir effect and the Lamb shift in hydrogen atoms. Near the event horizon of a black hole, Hawking showed that the extreme curvature of space-time can cause this process to have a permanently observable effect. In an oversimplified but intuitively helpful picture, a pair of virtual particles appearing near the event horizon might find one particle falling into the black hole while the other escapes. The escaping particle carries energy, and to conserve energy, the infalling particle effectively carries negative energy that reduces the black hole's mass. From far away, you would detect this as radiation emanating from the vicinity of the black hole. The technical details are more subtle than the virtual particle picture. The actual mechanism involves the quantum field theory of curved spacetime, but the result is clear and agreed upon by physicists. Black holes emit thermal radiation with a temperature inversely proportional to their mass. The less massive the black hole, the hotter it is. And over time, a black hole losing mass to Hawking radiation grows hotter and radiates faster in a runaway process that ends with the black hole evaporating entirely in a burst of high energy. For any black hole we know of, this process is absurdly slow at first. A black hole with the mass of our Sun has a Hawking temperature of about 60 billionths of a degree above absolute settlement. This is far colder than the cosmic microwave background radiation, which pervades all of space at about 2.7 degrees above absolute zero. This means that currently, every stellar mass and supermassive black hole is actually absorbing more energy from the background radiation than it's emitting through Hawking radiation. They are all, right now, gaining mass rather than losing it. Only in the very remote future, long after the universe has expanded and cooled below the Hawking temperatures of even the smallest black holes, will evaporation begin to dominate. And then the timescales involved are almost impossibly large. A stellar mass black hole with the Sun's mass would take roughly 10 to the 67th power years to evaporate completely. That is 1 followed by 67 zeros. The current age of the universe is about 1.4 times 10 to the 10th power years. The evaporation timescale for a solar mass black hole is therefore about 10 to the 57th power times longer than the current age of the universe. Numbers so large they lose meaning in any frame of reference connected to human experience. Supermassive black holes fare even longer. A black hole of 100 billion solar masses would take on the order of 10 to the 100th power years to evaporate. A googol years. That is a number so large that it exceeds the number of atoms in the observable universe by an enormous factor. Even the word astronomical fails to capture the scale. It is the kind of number that exists in mathematics but has no counterpart in anything physical that we have ever observed. And yet, if the laws of physics hold, every black hole will eventually end. In the very final stages of a black hole's evaporation, as its mass dwindles toward the Planck scale, its temperature rises exponentially and it releases its remaining mass in a final burst of high-energy radiation. This death is actually explosive. At the very end, a small primordial black hole evaporating today would release its energy in a final flash of gamma rays. Astronomers have searched for these evaporation bursts and haven't found any, which places constraints on the abundance of small primordial black holes in the universe. The evaporation of all black holes marks what cosmologists call the black hole era, the last epoch in the universe's history when there are still active macroscopic structures left. Before the black hole era comes the stellar era, which we are currently in. Then, the degenerate era, when only white dwarfs, neutron stars, and black holes remain. And then, the black hole era itself. After the last black hole evaporates, the universe enters what is called the dark era, a featureless, cold, nearly empty space where the only things left are photons, neutrinos, electrons, all separated by impossibly vast distances, all cooling toward absolute zero. It's a future so remote and so quiet that it almost feels peaceful. This vast perspective, from the formation of the first stars and the first black holes, through the long eons of stellar evolution, through the dark future where black holes are the last islands of structure in an increasingly empty cosmos, and finally to the silent epoch where even the black holes are gone. It puts our own moment in cosmic history in beautiful relief. We are here early. The universe is young. The black holes are still growing, still feeding, still shaping the galaxies around them. The long, patient decline is still billions upon billions of years away. We live in the age of stars and black holes, which is to say, we live in the most interesting era the universe will ever know. Part 10, we have already seen them. The triumph of the Event Horizon Telescope. Before we close this evening's journey, there is one more story that deserves its own moment, because it is one of the great scientific achievements of the 21st century, and because it transformed black holes from abstract theoretical objects into something almost intimate, something we have actually seen. For most of the history of black hole physics, these objects were inferred rather than observed. We could measure the gravitational effects of unseen, massive companions on visible stars. We could detect the X-rays from superheated gas spiraling into stellar black holes. We could measure the orbits of stars near the center of our galaxy, orbits that trace out paths only consistent with an object of 4 million solar masses contained in a region smaller than our solar system. All of this was compelling, overwhelming evidence. But it was indirect. Then came the Event Horizon Telescope, and on April 10th, 2019, everything changed. The EHT is not a single telescope. It is a global network of 8 radio observatories spread across 4 continents, from Hawaii to the South Pole, from Spain to Chile. By linking these observatories together and carefully synchronizing their observations, using atomic clocks to within a fraction of a millimeter in wavelength, the collaboration created an effective telescope with a diameter equal to that of the Earth. And with a telescope that size, the angular resolution achieved was approximately 20 microarcseconds, enough to resolve a grapefruit placed on the surface of the moon if you were standing on Earth. On April 10th, 2019, in simultaneous press conferences held around the world, the Event Horizon Telescope collaboration unveiled the first direct image of a black hole. It showed the supermassive black hole at the center of the galaxy, Messier 87, 55 million light-years away, containing 6.5 billion solar masses. The image showed a bright, glowing ring of light surrounding a dark central region. The shadow of the black hole's event horizon cast against the glowing gas of the accretion disk. It is a humble-looking image in some ways, blurry and orange-hued. Nothing like the crisp, imagined renderings of science fiction. But its significance is enormous. Here, for the first time in human history, was direct visual evidence of the region around an event horizon. The dark shadow at the center is the black hole itself, a region from which no light escapes. The bright ring is photons traveling so close to the event horizon that they have been bent into circular trajectories by the extreme gravity, before managing to escape to travel 55 million light-years and be captured by 8 radio telescopes on a small planet in an unremarkable corner of a medium-sized galaxy. 3 years later, in May 2022, came the second image, Sagittarius, A star, the black hole, at the center of our own Milky Way. This was in some ways harder to image than M87's black hole, despite being 2,000 times closer. Sagittarius A star is also 2,000 times smaller in mass. making it about the same apparent size in the sky, but the gas near it orbits much faster because the gravitational field is more compact. Gas takes days to weeks to orbit M87's black hole, giving a relatively stable target. Gas near Sagittarius, A star completes an orbit in just minutes, causing the brightness pattern to shift constantly during observations, like trying to photograph a puppy chasing its tail. The EHT team had to develop sophisticated new image reconstruction algorithms to account for this variability. But they succeeded. The image they produced shows the same essential structure as M87's black hole, a bright ring surrounding a dark shadow, but now centered on the black hole in our own galactic backyard, the one whose gravity controls the trajectories of the densest cluster of stars in our galaxy, whose jets and outflows have helped shape the Milky Way over billions of years. These images are not just beautiful and historically significant, they are scientifically important because they allow direct tests of general relativity in the strongest gravitational fields anywhere in the universe. The size and shape of the shadow, the brightness asymmetry in the ring, caused by the black hole's rotation and the relativistic beaming of approaching material. The dynamics of the gas in real time. All of these can be compared to predictions from general relativity. So far, in every comparison, Einstein's theory has passed with flying colors. The universe, at least in these extreme environments, behaves exactly as the equations say it should. This is not merely an academic validation. General relativity is the framework that GPS satellites depend on for accurate positioning, that gravitational wave detectors like LIGO depend on for interpreting their signals, that cosmologists depend on for modeling the expansion of the universe. Every test of the theory in a new regime is a check on the entire edifice of our physical understanding. And when those tests pass, as they have done so far at every opportunity, there is something deeply reassuring about it, a confirmation that the universe is lawful, that its deepest secrets respond to patient, careful inquiry, that equations scratched out on paper by a patent clerk in Bern in 1905 can describe the behavior of gas swirling around a 6 billion solar mass abyss 55 million light-years away. The next generation of the Event Horizon Telescope, currently being developed, will add more observatories to the global network and observe at multiple frequencies simultaneously. This will allow researchers to create movies of the gas near Sagittarius A star, tracking how it flows and changes in real time. It may eventually be possible to image the jets of M87's black hole in the same image as the shadow, tracing the full process from the event horizon outward to where the jet becomes the glowing, light-year-long structure we've been studying for decades. The science of black hole imaging is barely a decade old, and it is already transforming what we know and can see. Part 11. Black Holes and the Galaxies They Made. There is something we haven't yet touched on that deserves its own quiet moment of wonder because it fundamentally changes the way we think about black holes. We've described them, mostly, as destinations, as things to be reached, to be studied, to be experienced. But black holes are not passive objects sitting in the dark, waiting to be found. They are active participants in the cosmos. They have, in profound and measurable ways, helped shape the universe we live in. The relationship between supermassive black holes and their host galaxies is one of the most actively studied areas in modern astrophysics, and one of the most surprising findings of the past few decades. When astronomers began measuring the masses of supermassive black holes in a wide variety of galaxies, they discovered something unexpected. The mass of the black hole is tightly correlated with the properties of the galaxy's central bulge of stars, specifically with the velocity dispersion of those stars, how fast they're moving in random directions due to the combined gravitational effects of everything around them. This correlation is called the M-sigma relation, and it is remarkable because the black hole at a galaxy's center is tiny compared to the galaxy as a whole. The mass of Sagittarius, A star, at 4 million solar masses is a tiny fraction of the Milky Way's total mass of perhaps 1 trillion solar masses. The event horizon of Sagittarius A star is about 25 million kilometers across, while the Milky Way is 100,000 light-years across. These are objects of vastly different scales, apparently separated by an enormous gulf of distance and mass. And yet somehow, the properties of the tiny central black hole and the enormous surrounding galaxy are deeply correlated. The most widely accepted explanation is a process called AGN feedback, where AGN stands for active galactic nucleus. When a supermassive black hole is actively feeding, drawing in large amounts of gas and dust, it can release an enormous amount of energy in the form of radiation, jets, and outflows. This energy can heat the surrounding gas of the galaxy, disrupting the conditions needed for new stars to form. It can even drive gas completely out of the galaxy in powerful winds. In this way, the black hole regulates its own food supply. It feeds, releases energy, heats the gas, star formation slows, the gas supply dwindles, the black hole quiets down, the gas cools and begins to fall back in, and the cycle begins again. The jets of material fired out by active supermassive black holes are among the most powerful phenomena in the universe. The jet of M87's black hole, which we can observe extending for thousands of light-years beyond the galaxy's core, carries more energy than the combined output of billions of stars. At the end of such jets, where they slam into the diffuse gas surrounding the galaxy, they create enormous cavities and shock waves that heat the gas of galaxy clusters over enormous volumes. Some of the largest structures in the universe, enormous bubbles of hot gas detected in X-rays around clusters of galaxies, are simply the echoes of past black hole jets that fired millions of years ago and are still propagating outward. In the early universe, when the first galaxies were forming and the first supermassive black holes were feeding voraciously, this feedback was likely crucial in determining which galaxies grew large and which remained small, in setting the pace of star formation across cosmic history. In establishing the large-scale structure of the galaxy populations we observe today, black holes are not merely exotic objects of theoretical interest. They are architects. They have been actively participating in building the universe around them for billions of years. There is a beautiful symmetry here that is worth pausing on. Stars are born in clouds of gas and dust, live out their lives burning through nuclear fuel, and die, sometimes violently, as supernovae, returning material enriched with heavier elements to the interstellar medium. That material cools, collapses, and forms new stars. The galaxy is a cycle, and at the center of that cycle, in the most massive galaxies, sits a black hole that acts as a thermostat of cosmic proportions, periodically releasing energy that slows star formation, and then quieting again to let the gas cool and the stars form once more. We are products of this cycle in a very direct sense. The heavy elements in our bodies, the carbon in our DNA, the oxygen we breathe, the iron in our blood, were all forged in the cores of stars that lived and died before our sun was born. Those stars existed in a galaxy shaped partly by the feedback of its central black hole, the very conditions that allowed stars of the right size in the right place to form and shine long enough for planets to develop and life to emerge, were set in part by the intricate interplay between star formation and black hole activity across billions of years of galactic history. We are not just observers of the universe's black holes. We are, in a very real sense, downstream consequences of them. The universe that produced us was shaped partly by these extraordinary objects. Every breath you take, quietly, wherever you are resting, right now, carries atoms that owe their existence, in part, to the long, complicated dance between galaxies and their central black holes across the age of the universe. It's a lineage worth knowing. The next generation of space telescopes and ground-based observatories is poised to revolutionize our understanding of this relationship. The James Webb Space Telescope, launched in late 2021, has already discovered supermassive black holes in galaxies so distant and so early in the universe's history that they challenge our models of how they could have grown so quickly. Some of these black holes appear to be more massive than the galaxies around them, flipping the expected relationship. The universe in its infancy may have grown its black holes before it grew its galaxies, adding another layer of complexity to the story of cosmic coevolution. Part 12: Wormholes, Other Universes, and the Edge of Speculation. We've been careful throughout this evening to stay on the solid ground of confirmed science, of things we know and things that are well supported by evidence. But no, conversation about black holes would feel complete without at least visiting the borderlands, the ideas that are scientifically grounded but deeply speculative, the places where physics becomes almost indistinguishable from the most ambitious science fiction. And so, as you settle deeper into your rest, let's take a brief and gentle walk to the very edge of what physicists currently allow themselves to imagine. The concept of a wormhole, also known as an Einstein-Rosen bridge, emerged from the equations of general relativity almost immediately after Einstein published his theory. In 1935, Einstein and his colleague Nathan Rosen showed that the Schwarzschild solution, describing a black hole, actually had two ends. The geometry of space-time, according to the equations, didn't terminate at the black hole's singularity in the way people assumed. It could be analytically extended, and that extension revealed a mirror image on the other side, what would become known as a white hole connected to the black hole by a throat. In principle, if you fell into a black hole and survived, you might emerge from a white hole somewhere else in the universe, or even in a different universe entirely. This was purely mathematical at first. The Einstein-Rosen bridge of the 1935 paper is not actually traversable, as Roger Penrose and others later showed. Any traveler attempting to pass through it would find the throat pinching off before they could complete the transit. To hold a wormhole open long enough to traverse it would require what physicists call exotic matter, material with negative energy density. Negative energy is not entirely fictional. It exists in the quantum vacuum as the Casimir effect, but the quantities needed to stabilize a traversable wormhole are orders of magnitude beyond anything we can produce or even conceive of producing with known technology. Nevertheless, the idea took on a life of its own, both in physics and in culture. The term wormhole itself was coined by John Archibald Wheeler, the same physicist who gave us the term black hole. And in 1988, the concept became scientifically serious in a new way when physicists Kip Thorne, Michael Morris, and Ulvi Yurtsever published a paper in Physical Review Letters analyzing whether traversable wormholes were consistent with known physics. They concluded that while the energy requirements were extreme, there was no fundamental principle that prohibited traversable wormholes. The laws of physics, as we currently understand them, do not say no. This was the paper that Carl Sagan had earlier asked Kip Thorne to consult on, because Sagan was writing his novel Contact and wanted the faster-than-light travel in it to be, at least, somewhat physically plausible. Thorne's analysis not only served Sagan's novel, but opened up a new area of legitimate theoretical research. Since then, physicists have found wormholes appearing naturally in many theoretical frameworks, including certain solutions to string theory and in the mathematics of quantum entanglement. The connection to quantum entanglement is particularly intriguing and has become one of the most actively researched ideas in theoretical physics. In 2013, physicist Juan Maldacena and Leonard Susskind published a proposal with the catchy shorthand ER equals EPR. ER refers to the Einstein-Rosen bridge, the wormhole. EPR refers to the Einstein-Podolsky-Rosen paradox, the phenomenon of quantum entanglement, where two particles can be correlated in such a way that measuring one instantly affects the measurement statistics of the other, no matter how far apart they are. Maldacena and Susskind suggested that these two apparently unrelated phenomena might actually be different descriptions of the same underlying reality. Every entangled pair of particles might be connected by a tiny, microscopic wormhole in spacetime. This is deeply speculative, and it hasn't been proven, but it has generated an enormous amount of follow-up research. Because if it's correct, it suggests that spacetime itself might be built from the quantum entanglement structure of its contents, that the geometric fabric of the universe might be woven from quantum correlations. It's one of the more breathtaking suggestions in recent theoretical physics, a hint that the two great frameworks of 20th century physics, general relativity and quantum mechanics, might be unified through the study of entanglement and wormholes. There are also more exotic possibilities that physicists take seriously, at least seriously enough to study. The many worlds interpretation of quantum mechanics suggests that every quantum measurement causes reality to branch into multiple parallel universes, each one exploring a different possible outcome. Some theories of quantum cosmology suggest that the Big Bang itself might have been the emergence of our universe from within a black hole in a larger parent universe, and that new universes might continually be spawned inside black holes in our own universe. In this picture, the multiverse is an endlessly branching tree of universes, each one born inside the black hole of its parent. Lee Smolin, a theoretical physicist, developed a variant of this idea called cosmological natural selection, suggesting that universes with more black holes produce more child universes, and that the physical constants of each child universe are slightly varied from its parents. In this framework, universes would evolve over cosmic generations toward configurations with many black holes, which might explain why our universe's physical constants happen to be so finely tuned for the formation of complex structures and, eventually, life. It's a profoundly unconventional idea, but it has a certain elegant logic. None of these speculative ideas are proven. Many of them may never be testable in any practical sense, and testability is the bedrock of science. But they represent the leading edge of human imagination, guided by rigorous mathematics, the place where physics admits that the universe might be stranger and larger than our current confirmed models describe. And there is something genuinely wonderful about the fact that even the most conservative evidence-based science of black holes leads almost inevitably to ideas this extraordinary. As you rest here in whatever quiet space you've made for yourself tonight, consider that somewhere out there, right now, a black hole is bending space-time, drawing in gas that forms a disk of fire and firing relativistic jets across thousands of light years. Somewhere, two stellar mass black holes are spiraling toward each other in a gravitational waltz that will end in a merger felt as ripples through the fabric of reality itself. Somewhere, a star is wandering too close to a supermassive black hole and being stretched into a long, bright ribbon of torn stellar material, a tidal disruption event bright enough to briefly outshine its entire host galaxy. All of this is happening right now in an ongoing cosmic drama that has been playing for billions of years and will continue for trillions more. And we, on this small, warm world, have learned to detect the gravitational waves from merging black holes, to image the shadows of event horizons, to measure the orbital paths of stars being whipped around the invisible heart of our galaxy at thousands of kilometers per second. We have not yet reached a black hole, but we have, in a very real sense, already touched them. With our instruments, our equations, our mathematics, and our audacious insistence on asking the hardest questions, we have reached across the void and made contact with the most extreme physics in the universe. That is no small thing. A final thought before sleep. And so we arrive at our answer to the question we began with tonight. Can we actually reach a black hole? In the most honest assessment of where we stand today, the answer is no. Not with any technology we currently possess, or any technology that seems immediately achievable. The nearest confirmed black hole, Gaia BH1, lies 1,560 light-years away. At the speed of our fastest current spacecraft, reaching it would take more than 2 million years. The physics of interstellar travel is unforgiving, and the distances involved dwarf every timescale of human civilization. And yet, the answer is not a simple, permanent no. The physics of laser-propelled nanocrafts is sound. The exponential improvement in laser technology is real. The proposal by Cosimo Bambi and others for a century-long mission to a closed black hole is speculative, but not absurd. We may not be able to reach a black hole in the next generation or the next several generations, but the question of whether a civilization with centuries or millennia of continued technological development might one day send something to a black hole, that question remains genuinely open. What we can do, and have already done, is something in many ways more remarkable. We have seen them. We have bent radio waves from observatories around the entire planet, combined their signals with atomic clock precision, built algorithms capable of reconstructing images from sparse data, and produced actual photographs of the shadow of an event horizon from which nothing, not a single photon, ever escapes. We have done the impossible, as people said we couldn't. Twice. There is something about black holes that speaks to the deepest human impulse to understand, to push past the apparent edge of what's possible, to stand at the boundary of known physics and ask, what's on the other side? They represent, in the most literal physical sense, the limit of our knowledge. The event horizon is the place where information stops reaching us. The singularity is the place where our equations break down. They are, in every meaningful sense, the frontier of the known universe. And we are drawn to them. Not because they are dangerous, though they are. Not because they are destructive, though they are that too. We are drawn to them because the universe has, in its long and largely indifferent history, produced objects so extreme that contemplating them requires us to stretch and grow every concept we have about space, time, matter, and energy. To think about black holes seriously is to become a larger thinker. To grapple with the event horizon is to discover something new about the nature of information and time. To wonder about the singularity is to stand at the very edge of what physics can say and peer wide-eyed into the darkness beyond. Perhaps, someday, a probe we designed will cross the event horizon of a distant black hole and send back data for as long as it can, describing what it finds as spaghettification begins and the final moments of physics as we know it unfold. Perhaps that data will be the key that opens the door to quantum gravity and gives us, at last, a complete understanding of what lies inside. Or perhaps the black hole will keep its ultimate secrets forever, and the singularity will remain across all of time, the one place the universe refuses to explain. Either way, we will have reached for it, and that reaching, that perpetual, stubborn, glorious, human reaching toward the darkest and most extreme corners of the cosmos, is itself one of the most beautiful things in the universe. Tonight, let these thoughts drift gently into the background of your awareness. Let the image of that glowing ring in the darkness be the last thing you carry with you as your breathing slows and your body grows heavy and the day releases its grip on your mind. You are on a planet orbiting a star, in a galaxy that has a sleeping giant at its center, and the universe is vast beyond all reckoning, and filled with wonders so extreme and so beautiful that a lifetime of learning can only scratch the surface of them. And that's all right. That's more than all right. It's extraordinary. Sleep well. Thank you for watching. If this video found you in the right moment, if it gave you something beautiful to drift off to, something that made the universe feel both larger and somehow more intimate, then it has done exactly what it was made to do. I would be so grateful if you took a moment before you close your eyes or in the morning when you wake to leave a like on this video. It is the simplest way to let me know that this kind of content finds its home with people who need it. If you are new to the Science Pillow, please consider subscribing. Every video here is made with the same intention: to take the grandest, most wondrous questions of science and explore them in a way that feels like a conversation between friends rather than a lecture, a calm companion in the dark hours rather than a demand on your attention. Astronomy, the history of science, the mysteries of the human mind and body, the deep past of the Earth and the universe. These are our territories, and there is always more to explore. If you'd like to share this video with someone who loves the night sky or who lies awake wondering about the universe, or who simply needs something gentle to listen to, please do. The Science Pillow grows through word of mouth, one quiet night at a time. Thank you for being here. Thank you for your curiosity. And thank you for spending part of your evening in the company of black holes, those impossible, magnificent, endlessly fascinating points where the universe folds in on itself and keeps its deepest secrets. Until next time, rest well and keep wondering.